Alright, so today you're going to be finding a particular solution to a differential equation when we have an initial condition. And so example 1, we have the differential equation and the general solution for it. So the differential equation is dy over dx equals x over y, and it has already been solved for the general solution, and it's y equals positive or negative square root of x squared plus c. And so we're going to let y equals f of x be a particular solution to the differential equation with the initial condition that f of 5 is equal to negative 4. And so what we're going to do is just plug in those values, and then we'll be able to find c, and then that will give us the particular solution. And so y is going to be negative 4. Now, when you give a particular solution, you don't give the positive and negative answer, you just give one or the other. And so when you look at this, negative 4 obviously has to equal a negative square root. So the value of positive or negative of the initial condition is going to tell you if you're going to do the positive or negative square root. So in this case, we have to do the negative square root, and then we're going to put 5 in for x. All right, and then the negatives kind of cancel each other out. And we want to solve this for c. And so what we would need to do at this point is to square both sides. And then when we subtract the 25, we're going to get that c is negative 9. So the particular solution is y equals, and then we already determined is going to be the negative square root of x squared minus 9. Oh, sorry, we're supposed to call it f of x. Okay. All right, so on example 2, we're going to have to do all the things. And so we are going to have to find the antiderivative and then plug in. So the first step in solving a differential equation is to separate the variables. So in this case, we're going to need to divide by y squared and multiply by dx. Okay, so because there is something in the denominator and the power of it is not 1, we would rewrite that. Okay, and then we're going to integrate. So add 1 to the power and divide by the new power. All right, so when we integrate just dx, that's just like integrating 1 dx, which is just going to give us x. Now, what I do, and I'm sure there's different ways to do it, but I like to, as soon as I have a c, plug in the initial condition. Okay, and so x is going to be 1 and y is going to be 1. So y to the negative 1 means obviously y in the denominator. X is also 1. Actually, let me rewrite that for a second, sorry. Let me write it with y and x so it's not too confusing. Okay, so now I'm going to plug in the initial condition, which is 1, 1. All right, and then when I solve that for c, I'm going to subtract 1, so it's going to be negative 2 is c. All right, and so what that means is I'm just going to go where I have a c, I'm going to change it to negative 2. Now I've got arrows going everywhere. All right, and then now I just need to solve this for y. So I'm gonna just flip it over. So if negative 1 over y is equal to this, then I can do the reciprocal of each side. And then multiply by that negative 1, and y should be negative 1 over x minus 2. Now, if this is a particular solution, I should be able to put in the initial condition and get a true statement, and I do. And the derivative of this should be that. All right, let's look at this baby bird question. So this baby bird that we've actually talked about before, the rate at which it gains weight is proportional to the difference between its adult weight and its current weight. At time t equals 0, when the baby bird is first weighed, is 20 grams. If b of t is the weight of the bird in grams at time t days after it is first weighed, then db over dt is equal to that differential equation 1/5 times 100 minus b. We're going to use the separation of variables to find y, which is b of t, is the particular solution to the differential equation with this initial condition. Okay, so the first thing we're going to do is separate the variables. So I'm going to get my b's on the left side and my t's on the right side. And I'm going to leave 1/5 where it is. All right, then I'm going to integrate. Okay, so let's look at this for a second. We've talked about that. If the derivative, or just when to use u substitution. If you think you need to use substitution and the derivative is 1, then no. What you think would be u is the derivative of that is 1, then you're not going to do u substitution. In this case, this isn't just a b, it's 100 minus b. The derivative isn't 1, but it's negative 1. So if that's the case, we could do u substitution, but it's so much easier if we just multiply by the reciprocal of whatever that derivative is. So if you take the derivative of something you might use as u for u substitution. And get a constant. Then just multiply by the reciprocal of that constant in front of the integral sign. So it would also work if the derivative of that thing was 2. You would just multiply by 1/2. So in this case, the derivative of this with respect to b is -1. So the reciprocal of -1 is just -1, or a negative. So if I do that, then I don't have to worry about any of the u substitution, and it just makes it a lot easier. And don't stress about this. We're going to practice a whole lot like this. All right, so now when I find the antiderivative of 1 over something with a dv, it's just going to be the natural log of that something. All right, and then on the other side, the antiderivative of 1/5 dt is going to be 1/5 t. And then just make sure you don't forget about that plus c. Okay, and then I like, as soon as I have a c, to find what it is by plugging in the initial condition. All right, so my initial condition is 0, 20. So I'm going to put 0 in for t and 20 in for b. And that is going to make c equal the natural log of the absolute value of 80. Well, the absolute value of 80 is 80. And that's okay. C can be a natural log. It's fine. All right, and then as soon as I have C, I'm going to plug it in. Okay. Now, this is a logarithmic equation, and I am going to need to write it in exponential form to solve, but because this negative is in the front, I'm actually going to need to move that, divide through by a negative first. Then I'm going to write in exponential form. Okay, so it's going to be e raised to the negative 1/5 t plus natural log of 80 equals the absolute value of 100 minus b. Hopefully we can squeeze all this on here. Okay, now I don't like that being on that side. Now I'm going to go ahead, and we talked about this before, I'm going to go ahead and change this because I know that to get addition for these powers that I multiplied two things together with those powers. And then I hope you also remember from either Algebra 2 or pre-calculus that when you have e raised to the natural log of 80, the e and the natural log will cancel out, and that just ends up being 80. Okay, so now normally, like if we didn't have an initial condition, we would need to do the positive and negative because of this absolute value. However, I can only do one or the other. And so if I plug in my initial condition, I'm going to not write this down like permanently, if I plug in my initial condition, -1/5, it ends up being just 0. Oh, shoot. Okay, sorry. 100 minus 20 equals 80, e to the 0. E to the 0 is 1, and so I do need to get positive 80 equals positive 80. So in this case, we can drop those absolute value bar, and it's only equal to the positive, not the negative. Okay, and then I just need to solve this for b. So what I'm going to do is I'm going to add b. And then I'm going to subtract the 80 e to the -1/5. All right, so that is my solution. All right, and then it would be a good idea just to double check your initial condition. If I put 0 in for this t, this whole exponent is 0, so this whole thing becomes 1. And then 100 minus 80 does give me my 20.